Howdy, everyone. So everyone had a fairly exciting morning? That's good. It's good, because now you're stuck in a room with a talk which I would say the explicit goal is to be the most boring talk at Lambda Jam. Lock the doors. So let's get stuck in. Mundane utility is an interesting turn of phrase, and it reminds me of functional programming in a lot of ways. The idea that you can have extraordinary powers but do something extremely ordinary with it. When I hear people talking about functional programming, they're always talking about the crazy, amazing things we can do with functional programming, or what is the magical, most complicated problem I can solve to justify using functional programming. I'm kind of interested in the other side. So I work with a team of about 15 to 20 people. We're writing Haskell every day, doing functional programming every day. And most of the problems we're solving are plain old programming problems. They are the mundane. We want to be able to do really well at those. So the most mundane thing I could think of is UNIX. Supposedly there is somewhere in the vicinity of 1.5 to 2 billion UNIX installs right now. Probably like, how many people are in this room? There's probably 2 per person in this room. There is a lot. Who uses or Unix or Linux or some variant day to day? That's good. That's going to make this talk a little bit easier. Cool. So Unix has a fairly simple architecture that I'm going to dramatically simplify even more, just for the purpose of introducing things. But Unix, we have a Unix kernel, abstracts over our hardware, provides us a bunch of services to userland programs, so we can go and implement programs that can do all sorts of various things. One of the most interesting things about Unix's design, which kind of set it apart when it was when operating systems were in their infancy, was that the user shell, or the interface to the actual operating system, was separate from the kernel. It exists in userland. That means that we can replace it. We can use a different one. We can even write our own. So hands up here, who uses bash day to day? Everyone take note of those people. Who uses Z shell? Yep, laugh at the first people. No, it's okay, it's okay. Who uses fish? Oh, got a couple of people. It's cool, cool. Who uses something simpler, a traditional corn shell or something like that? Nobody? It's all right. Who uses seashell? One person. Yeah, even bash users can laugh. No, sorry. But the point is that there's a whole variety of shells providing a whole bunch of different functions, providing a whole different view on our operating system. The purpose of this shell is to provide an interface to all of the utilities that we have, and really provide a way to compose programs. And what I mean by compose programs is, rather than coupling programs by writing a program that references these two things, being able to compose programs just through their data. And Unix shells let us do this. And they are quite painful, but they do let us do it. So, as a bit of a framework for understanding where shells fit in, let's talk about how we get to a shell running on a computer. So, we start with piece of hardware that's going to run some firmware. Traditionally, this would be BIOS. More modern systems might have UEFI or something else. That firmware will load a bootloader. This is where all of the get off my lawn programmers can go, yeah, nobody can fit it in the space required anymore, and I have bootloaders that load bootloaders and all crazy sorts of stuff. Bootloaders are responsible for loading our kernel. And our kernel is responsible for setting up our system, configuring our devices, etc., but then starting one process and one process only. That process is generally what we refer to init, even though it comes in many forms, is the source of many wars. Exactly what init is. In modern Linux systems, we have sys5, we have traditional init stuff, we have systemd. On FreeBSD, we have an RC system. There are a whole bunch of different ways. And then init is responsible for starting other processes. Okay? How does it start another process? Well, it has to ask the kernel to do something for us. The kernel doesn't provide any way to say, run program. That's not a function that the kernel gives us. Instead, we have to look out for replicants. But what we do is we ask the kernel to copy us through the fork call. So have a look at the fork call. This is very relevant for when you're implementing your own shell this afternoon. Hopefully people are going to come to the workshop, which is kind of the point. So fork creates a new process. A new process is an exact copy of the calling process. That's interesting. So init's going to create an exact copy of itself. It's not all that useful, but we can do that. So we're going to create an exact copy of ourselves. And then we want to turn that copy into a different program. So we get provided with a different system call, which is exec. Exec will take the current process image and load in a new executable into that space. So that's like Terminator, T1000 type stuff. And so we can turn our forked process into another process using exec, or the exec family of functions. This is just one example of how we could get to an actual shell running. This is how FreeBSD works. But there are many other ways. There can be graphical shells and a whole bunch of other things. So FreeBSD, in it we'll call the Getty program, which will do a bit of housekeeping on our consoles, our terminals, to make sure everything's right, which we'll call the login program by fork and exec again. The login program will prompt us for a password. Once it authenticates us, it will look up our shell and then invoke our shell, again, using exec, replacing the login program. We'll get a shell, and then using this shell, we can start programs, we can run programs in the background, we can do a whole bunch of things as users. So I can run ls, I can do a whole bunch of different things, right? So that's where shells fit in. Shells are now responsible for starting our other programs, etc. On OS X, there's a graphical shell, but we also have command line shells. When I say shell from now on, I'm probably going to be referring to command line shells. Cool. So what is a shell and why would we want to implement one? So the why is kind of interesting. One of the reasons might be that we have vulnerabilities that get their own graphics. This is shell shock, which is a bash vulnerability that allowed remote code execution for a whole bunch of different things. I also put this question to my team about like what's wrong with shell. We write lots of shell and hate it quite a bit, but apparently everyone on my team has either dropped a production database, and if they haven't done that, they've deleted all source control ever. One of the two. There are lots of different ways. This poor person who, on the internet, changed their install scripts to run rm-rf/user and added an accidental space. You can't actually even get to the code anymore. There's so many comments on it. There are lots of different reasons. A more modern issue is, or not even a modern issue, it's something that's happened for ages. How many people have a git prompt that displays the branch name? Yeah, poor people. So most implementations of this call eval, running arbitrary code. The default branch on a Git repository does not have to be master. It could be a specially crafted branch name that when you cd into the directory will execute arbitrary things on your computer. Just good luck with that. Okay. There are lots of reasons for us to implement our own shells. They're error prone. We use them a lot, and they are pretty critical. Maybe we can do a better job, whether it's a better job through adding better support for linting or checking scripts, or it's actually implementing a shell that is less error prone or provides more functionality to write correct program compositions. Cool. So building blocks of a command line shell. Start at the bottom. The first thing that a shell has to do is line editing, or some form of line editing. So this is interacting with console and taking user input. So when you hit backspace, it will send an escape sequence, turning that escape sequence into actually deleting a character in your console. Line editing functionality also tends to look after things like history. auto completion or tab completion, being able to do replacing on previous commands, etc. Then we have command parsing. So that's taking the string that you give your shell and turn it into a program to execute or a series of instructions. Command expansion, which is taking that parsed command and doing things like filling in variables, running subshells, doing globbing if you're into that sort of thing. Providing a series of built-ins. If you do the workshop this afternoon, you'll see why built-ins are important. There are some things that can't be done sensibly via forking executing a program. CD is a good example. So they provide standard functionality like CD, setting of environment variables like a whole bunch of other things that I'm not thinking of right now. And then process management, which is kind of the crux of the problem here. Starting and managing processes. This is the basics of just running a program, constructing a pipeline or a list of programs to run, and through to job control. So being able to start things in the background, recall them, disconnect them from your terminal, that type of thing. Cool, so I'm going to explain line editing first in about 3 seconds by saying we're going to cheat. Line editing is a mundane problem, but it's not the mundane problem that I want to tackle today. Most shells do use another library or a dependency to implement line editing. Bash uses GNU readline, for example. We're going to take a similar shortcut. If in the workshop you would like to implement your own line editor, it is possible using Haskell has a dependency called terminfo. You can try to do that yourself, but I'll demonstrate what we have. What have we got? So, going to use Haskell line, which is a GNU readline clone that kind of get input line. We're going to parse that input line and then go and interpret it. So nothing too complicated. But that gives us the ability to, if I run that, that's the test. Oh, it's probably a bit small, sorry. So if I run that, so get a prompt, things aren't implemented, I can't actually edit anything. Oh, sorry, it exited. But we'll get there in a second. So we have line editing, and if I run it again, we'll have history once we can run a command. So moving on to more interesting things. Parsing. Here is a domain that is somewhat optimized for the tools that we have in functional programming. We have good data type support. We have good parser support. Haskell in particular has lots of really good parsing libraries. So we're going to dive into this. So I'm going to present a quite simplified grammar of a shell that's based on Bourne shell but without control flow for the moment. You can do a lot with it. So to kind of give you an idea of what we want to be able to do. So we want to be able to, this is in Z shell, but we want to be able to do things like, say, echo. So run a program. We want to be able to pipe that program into something else. So maybe said, we want to be able to do pipes. We also want to be able to say we want to be able to do things conditionally. So that will fail. So I want to or echo that was bad. Right. So I want to be able to have ors. I want to be able to have ands. So that's not going to echo because it's false. Right. So ors, ands, pipes, and then I also want to implement multiple programs, so semicolon, so I can then output something else as well. Okay, so that's kind of the complete version of our baseline shell, and we can extend from there. So, parsing. We're going to follow a fairly well-trodden path for how to construct the parser. There are a few challenges in doing it for a grammar like this or for a POSIX-like shell. But we're basically going to follow these steps. We've got some character input. We're going to lex that into a series of tokens, which are our and, or, pipe, statement terminator, and our words, which make up our program. Once we've got our token stream, we'll take that, run it through a parser to actually construct a program tree that we'll be able to interpret. So it's quite straightforward, but as you see, working through it, there's a few interesting problems to solve here. Cool. So let's get in and get started. Make sure I'm compiling. Cool. So I've got a whole bunch of tests which are going to fail. So I'm going to start with Alexa. Cool. Or they're not all going to fail, apparently. Cool. So I'm going to start with data types. Sorry, a bit all over the place. Okay. So as I said, our token stream is going to be fairly straightforward. To implement these types of programs, we need an AND token, an OR token, a statement token, pipe token, and the most interesting one, which is our word token, to construct our programs. From here, so we can go in, yep, looks fairly reasonable. We can go and start to implement these things. Bring that over. So we want to be able to construct tokens one at a time. So how we're actually going to do this is we're going to read or consume a token, and then for any space after that, we're going to discard that space. So that's how we'll get rid of things like comments. We'll chew up any space. If there's a comment, we'll chew it all up until we hit a new line or another token. So that's what space or comment's doing, which I've provided. Won't go into too much detail. So now I want to handle AND tokens. Start with all the easy ones. OR tokens, statement tokens, pipe tokens. So they're all the obvious ones. Starting to get less obvious. We want to handle end of lines. So going to follow a very simplified model. People who actually write programming languages don't hate on me too much, but we're going to do pretend semicolon insertion. So every time we see a new line that's not as part of a token, we're going to insert a semicolon to indicate that that's the end of a statement. Okay, so that's a little bit cheating. And then we're going to do our words, which I'll have to explain a little bit more detail. Cool, I'll get there. Cool, so hands up if people think they understand how a shell parses words or parses their command line. No? No one's even that game. Cool. That's pretty good. So I've got a simple test program. So printf, which is what works like a C or a Java or Haskell printf, it's just going to print one argument. For each argument, it's just going to print it out one at a time so we can kind of see. So if I type foo bar, I have two arguments, foo, and then space is the limit of that token, bar is our second token. Okay? People will be familiar with soft quotes, double quotes. We'll turn foo and bar into a single token. We've got hard quotes, single token. This is where things starts going a bit crazy. So this is where people start getting confused. So what if I want to have a variable here, foo equals, and then I actually want to print foo, and then I want to do something else. I'll actually define foo for a second. So how many actual tokens are here? I've got a hard quoted bit, I've got an unquoted bit with a variable and some soft quoted bits. Anyone want to yell out how many tokens are here? One? Good. Somebody. Cool. What am I doing? Oh, no, that's right. Yeah, so one token, right? I can put quotes around any part. I can, I don't know, end up with all sorts of ways, all sorts of different ways to interleaving hard quotes, interleaving soft quotes. So hopefully that makes sense. So it's quite a complex tokenization problem. If we go to the spec for the real tokenization, which looks, there's a wall of text followed that doesn't actually explain anything about how to actually do it, followed by the grammar, which again only shows about half of the things, and you have to read about 40 pages to actually get to the end of it. So we're going to use data types to kind of drive out a sensible way to handle this problem. So what we're going to do is, I've got a picture for it, so that. We're going to say that words can be made up by any series of either soft, hard, or unquoted parts. For soft quoted parts, we can either have soft quoted text or a soft quoted variable. In a real shell, you might have other things such as subshells being a child under here. We can have hard quoted text. For unquoted things, we can have variable or text. In a real shell, you might have globbing or other things in here as well to parse words. It's really important that we handle this word recognition as a part of lexing. It's very difficult or impossible to do later on when you have to do recursive execution for things like have a variable and then that variable has a subshell in it and you want to execute that and it gets quite hard. Cool. So that should be reflected in our types. So our word type is basically a list of part. That up the top maybe. List of part. Part can be hard quoted, which is just text. Soft quoted, which is a list of fragment. Or unquoted, which is a list of fragment. And then a fragment can either be a text part or a variable part. So we can go in here. We can start to look at just quickly this. Beautiful. There we go. So parse. So I'll try to build this up slowly. So we can parse our simple program like echo hello world. We can add in, bring up the top so people can see it, add in things like other programs. Missing quote, see? So things even work. So we can tokenize this stream into a series of words. So we have, well, we've gone a little bit further, parsing everything. We'll get to that in a second. Cool. So back here. Cool. Okay, so now onto our actual parser. So look, starting again at the data types. We've got some complex rules. So as I've kind of tried to allude to, we have a simplified grammar, but this grammar is that we have a program, which is a list of lists, a list being a shell term, a list being a series of commands. A list can either be a singleton list that contains a single pipeline, an AND list, which is two pipelines separated by our AND token, or an OR list separated by the OR token. This is quite a funny or looks a little bit odd to be defining it like this. So we have a recursive list-like structure that has list, except instead of normally we would say our head, which would be the pipeline, and then the list, which is the rest of the things to come. These are flipped over. That is because if you look at normal shell, things are left associative. So if I bring up my example from before, one of these examples, the parentheses go here. If we were to define this with a normal data type and parse it in a normal monadic parser, things would be right associative and we'd end up with quite odd behavior. I'll try. Might end up with something like that, which is not what you want. I'm not sure if hopefully that makes sense. So we really want to make sure that everything's left associative with parsing. Don't have to define the data types like this, but it definitely makes it easier. So we have a list, which is made up of pipelines or ANDs and ORs, and then a pipeline, which is made up either of a single command or a command separated by a pipe. And then our commands are just a list of words. Cool. Okay, running a little bit short on time, so I'll fly through process management, get to the bit where we can actually show something working. So, simple pipeline, so ls, sort, unique. It's kind of our final problem that we're going to solve for our base level shell. There are many different ways in which you construct the processes using fork and exec to achieve this. One of the most traditional processes is that we follow this process where we'll fork our shell once to start the very last thing in our pipeline, and we're actually going to wait on this process. That process will fork itself for the first child and exec to create ls. Will fork itself, exec to create sort. We'll construct a pipeline between ls and sort, and a pipe between sort and unique. And we'll wait for unique to return, so you wait for the last thing. This is traditionally how a lot of early shells do it, and it's very good for resource management. Actually calling fork and execs, looking after file descriptor handles is quite a challenging problem, and this turns out to be a fairly nice way to do it. Final exec. An alternative way that often a lot more modern shells, I think Z shell, this is the process that Z shell follows, is that they have a much more normal process where you fork once, which will then fork again, exec the first thing in your pipeline, exec the second thing in your pipeline, exec the third thing in your pipeline, wait for that result. So it's a slightly different formulation where the forks happen, what resources you have to clean up. We're going to do a third version that's even simpler than that. We're going to fork 3 times from our parent process. We're going to call fork, and then exec for our first process, fork, and then exec for our second process, fork, and then exec for our third process. This is a little bit heavier on resources, and maybe not how you really want to implement a real shell, but it has some nice properties. One of the nice properties is that the parent shell has access to all 3 childs. So that means you can implement things like bash's pipe fail. So if you have a pipeline, you can actually detect if any part of it exits with non-zero rather than just the last component, which is a nice property. Cool, so quickly go in and implement this. Just make sure I'm compiling. Cool, so run pipeline. So we have, just going to work down from the top. I should start at the top. So we have a program that we're going to interpret. So how do we actually do that? Let's start with that. So we have empty program. We just want to return exit success. We don't want to do anything. If we have a single list in our program, we're going to run list, passing in our input, our output, and our error stream, and run that list. If we have more than one thing, we're going to run the first one, and then we're going to recursively loop with the rest. So this is very mundane program. Not working out for me, is it? Oh, it's all right. I'll get to that in a second. But this is a case of just following the types. We've constructed our types so that it's as easy as possible to run through the interpreter. I'll zoom through this until we get to the interesting part. So now we're going to do our lists for a singleton pipeline. We just have one pipeline. We just need to run the pipeline, input, output, and error stream, and run that pipeline. For the AND list, we want to do something slightly more complicated. So we wanted to get our result from running the pipeline. By running our parent, sorry. And then we want to check on that exit case. If it's AND and it's success, then we actually want to run the second one. So we want to call run list. Run list on the parent. Run pipeline on ourselves. Otherwise, we just want to fail how we did. Very similar process for OR, obviously. Run list on the parent. If it's this case, if it's success, then we want to stop with that exit code. If it fails, then we want to run the pipeline. That going a little bit longer than I'd like without compiling because of this bit, so I'll get to this bit. Singleton pipeline, we just want to run one command. One run command with input, output, error, and the command. And I'll just put an error here for a second so I can explain something. Hopefully that all compiles. Yep, cool. So we've kind of done nothing complicated except walk through the types as simple as possible. We've implemented and or as I've been walking through this. Now we're up to the compound pipeline. So I just have to introduce one quick concept to implement the compound pipeline correctly, and that's the idea of an actual UNIX pipe. So a pipe creates a unidirectional conduit with a read side and a write side that we can use to communicate data from one process to another. Okay? Calling the pipe function will create one of these these two file descriptors and the pipe. And the interesting property of these things is that they won't return end of file until all of their input or all of their output have all been closed. So that lets you do things like pipe the output of cat, two different cats piped together. So you can kind of see that if I go echo foo, echo bar, pipe to cat. If, for example, if echo foo is going to return the end of file, echo bar is going to return end of file, maybe if it was cat. If cat responded to those end of files, it would have just printed echo foo. But this pipe actually doesn't return end of file until all of the inputs that have been chained all close their pipe. So that's interesting. That's what lets us actually implement piping functionality. So we want to create a pipe. So read, write, create process, create. Okay, once we've got a read and a write side, we're going to cheat a little bit. So I'll dive into run command to explain why. So I've chosen not to implement, use raw fork and exec commands from Haskell just for the purpose of this exercises. So we're going to use system.process, which internally in C implements fork and exec. The reason for this is just to simplify it. There's a challenge exercise to go and implement fork and exec yourself if you would like. But this makes it easier. So what we're going to use is control concurrent async to asynchronously execute these two processes, which will make it a lot easier. So we're going to do this. Our first exit code, our second exit code. So async dot concurrently. We want to run pipeline of, so get the input. We want to write to the output side. Keep error on our parent. And on the other side, we want to run command, given it the read of the pipe, going to output and error on the command, like so. And then return the final steps exit code. Notice that I'm ignoring underscore EA here. This is where I mentioned before pipe fail you'd execute if you wanted to check both exit codes. Just make sure I've typed everything correctly. Cool. So now we should be able to fire up an actual shell. If I go into the right thing. Cool. Cool. So now I should be able to echo foo in our own shell. That's going to work. We could echo foo pipe grep, pipe sed, swap, foo, bar, whatever we want to do. And we've got pipelines and they implement it and they work. And exits. Everyone who implements this the first time might have that hang if you don't do it properly. Get ready for Control C. We can also do something. I've also constructed some scripts. So just some simple examples of pipe, for example, using our shell, X shell in the env-line. So we should be able to, we've got enough implemented that we should be able to go and run these scripts as well as work with it interactively. maybe. Cool. So you can see it's implemented echo script and the pipeline script, done some work. So we've implemented a somewhat real shell. Cool. So just to finish off, probably way past time, but I'm getting the bad nod. I'll just say, we'll talk about it more in the workshop this afternoon. You get in. For the beginners, I'll get you to step through the bits that I've already done. For more advanced people as a branch to jump ahead and implement some more features. I want everyone to push the limits for me. So there's a whole bunch of things that you could do. You could take it in a path that leads to creating a fish-like, more interactive shell, maybe doing fuzzy find. You could implement a whole bunch of utilities like a concurrent for or parallel for. Implementing like first-class parallelism in a shell would be pretty awesome. Having things like race to processes, etc. That would be pretty awesome. You could implement a linter on top of our parser, which would be also pretty cool. Or you could just keep trying to get POSIX equivalent, see if you can outdo Bash. So everyone can put their hands down. Cool. Workshop 115. Thank you.